Hello, my people. Hope you're doing well. This is the third video for our day one activities, festivities, if you want. I said in the last video that we would start with one last arc length problem. I decided against it. We're just going to go ahead and hop into the next topic here. And when we're dealing with radii and theta and stuff like that, we will occasionally not only be dealing with arc length, but arc length per time, right? So let's go ahead and look at the definitions that Larson has given us. It says, consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed v of the particle is arc length per time. Now, if you think about it, if you can measure a distance, and that distance is traveled in a period of time, then, if you can measure miles, then you can also measure miles per hour, okay? So all we're doing is we're taking arc length, which was r times theta, and when we're basically talking about it in terms of a measurement of time. So we could have, we could go back here and talk about the minute hand of the clock and the fact that it actually moved from the 12 o'clock to the 2 o'clock. It moved 8 pi over 3 inches. But it moved that distance in a particular time, right? And therefore you could take that, and of course it's a clock, so it doesn't matter how far it moves, it's always moving at the same speed, right? So for a clock, the linear speed and the angular speed will be a constant. But we could have calculated it. We could have said, well, 2 o'clock, from 12 o'clock to 2 o'clock for the minute hand is 10 minutes, right? And so we could have taken this and divided it by 10 and called it 8 pi over 30 or 4 pi over 15 inches per minute or something like that, okay? And that's the general idea of what we're doing here. Now notice that it gave us the formula as s over t. But we need to remember that s was r times theta, so it's actually r times theta over t. Or when you take into account my angular speed down here, which is not linear distance per time, but just how much of an angle is swept out per time, that theta over t right here times r means that my angular speed, omega, r times omega is also the linear speed, okay? And of course, I've sort of gotten ahead of myself, but let's go ahead and read that second portion of it. Moreover, if theta is the angle in radian measure corresponding to the arc length s, then the angular speed, omega, of the particle is theta per time, right? Theta over t. And that, thing is that, we can measure theta, and we can measure theta as a rate per time. We can measure linear distance in terms of arc length. And then, of course, we can measure it per unit of time, okay? And so neither of those should be really, really surprising, but let's go ahead and see how they actually work, okay, in terms of a couple of problems. Says a water wheel has a radius of 12 feet, and the wheel is rotating at 20 revolutions per minute. Find the linear speed in feet per minute of the water, okay? So the water wheel has a radius of 12 feet. Here, where's my black pen? Okay. So here we have, this is a radius of 12 feet, okay? The wheel is rotating at 20 revolutions per minute. Well, 20 revolutions doesn't really give us a theta measurement, but it's only one step away from giving us a theta measurement because 1 revolution is 2 pi. 20 revolutions is going to be 40 pi. Okay? And so basically what happens here is the wheel is rotating at 20 revolutions per minute. Okay, so 20 revolutions per minute can be transformed, and a revolution is 2 pi, right? Can be 40 pi radians per minute. Now, what kind of unit is that? What kind of measurement is that? That's an omega measurement, right? Because that's a theta per time. So this is omega. And as we said before, you know, if linear speed is arc length over time, it's r theta over time, but it's also r times the theta over t, or r times omega. So at this point, we want to take into account the fact that my linear speed, or v, is equal to r omega. My radius, I've already been told, is 12 feet. And now I figured out that my omega, simply by converting revolutions into a radian measurement, 40 pi radians per minute. And again, we're going to see radians disappear as a unit once we've done our multiplication. Now, 12 times 4 is 48. 12 times 40 is 480. So 480 pi feet per minute. And that is exactly feet per minute. That is exactly the units that I was being asked for. Now, if they actually, because 480 pi, when you're dealing with distance, you know, you're like, well, pi is a little bit more than 3, so, you know, maybe I ought to turn that into a decimal. And we can, and it's relatively easy. Just put 480 pi into your calculator. And remember, we're estimating to 3 decimal places, 1507.964 feet per minute. And that, of course, is my linear speed. Okay, well, let's take a look at another problem, okay? Keeping up with the sun, okay? Now, how fast would you have to travel on the surface of the Earth at the equator to keep up with the sun, okay? That is so that the sun would appear to remain at the same position in the sky. Now, I cut and pasted this from a worksheet, and but what we need, and I forgot to give you the measurements of the Earth, but basically the Earth, if you didn't know this, is approximately 28,000 miles in circumference around the equator. I think that's right. And it's somewhere in that neighborhood. And we'll use that measurement for now, and I'll try to be a little bit more careful when I'm cutting and pasting in the future. But we know that 28,000 miles represents the arc length, right? It represents the circumference around the equator of the Earth. And so 28,000 miles, okay, and we travel that, of course, that basically goes around every 24 hours, okay? So, and the question probably gives it to us. The question probably gives it to us and gives us the radius of the Earth. The radius of the Earth, let's see if we work backwards. I think it's something like 4,000 miles. Yeah, I mean, this says it's about 4456, okay? So if you were to want to calculate the radius based upon this measurement. But, you know, I think it's important not only to remember the fact that V is equal to R omega, but that it's also equal to S over T, and it's equal to R theta over T. I mean, all three of these are legitimate ways that you could be given the information and asked to discern the value for V. In this particular case, it actually winds up being really straightforward, and we have v is equal to 28,000 miles over 24 hours, and therefore it's going to be a little over 1,000 miles, right? And so if you were actually, you could reduce that, of course, because 24 and 28 have a common factor of 4, and so that would be 7,000 over 6. But let's just go ahead and put 28,000 divided by 24, and we wind up getting, 1166.667 miles per hour, and that is going to be our linear speed. Now, let's look at a couple of problems that actually give us a scenario and ask us to calculate both the linear speed and the angular speed. Okay. A record is spinning at a rate of 25 revolutions per minute. Okay. A record player. I don't know. Yeah, I'm sure that you've seen movies. You've seen them in movies. A record is spinning at a rate of 25 revolutions per minute. If a ladybug is sitting 10 centimeters from the center of the record, what is the angular velocity of the ladybug? Okay. Now, if a record is spinning at 25 revolutions per minute, that is not radians per minute, but it's close, right? It's close to being radians per minute, and I don't know if you learned this in chemistry, but one of the great things about chemistry is they give you those little conversion things, and you can say, okay, well, that's 25 revolutions, if you need to do a couple of different things, revolutions per 1 minute. Now, I am looking for angular velocity in terms of radians per second. So revolutions need to become radians, and minutes need to become seconds. So you need to change two things, and putting it in a chart like this is actually pretty helpful. I know that 1 revolution is equal to 2 pi radians, and I put it like this specifically so that the revolutions will cancel out. I also know that 1 minute, and I do it this way so that minutes will cancel out, is equal to 60 seconds. Okay? Minutes go bye-bye. And now all I have to do is just multiply straight across, and I'm going to get 50 pi over 60 radians per second, which of course reduces to 5 pi over 6 radians per second. And we, of course, have our answer to the first question. Which actually didn't require us to really riddle anything out. It simply required us to convert a rate that we were given into the rate that it was seeking. But if I want to take that and figure out what speed, the linear speed, that the ladybug is spinning around while sitting on top of this record, and I need it in centimeters per second, I need to recognize the fact that this is, of course, omega. Okay, that is my angular speed. It's my angular speed. And in order to get my linear speed, I need to multiply omega times the radius. Now, it doesn't tell us the radius of the record, but I'm not really worried about how fast a point on the edge of the record is revolving around. It tells us how far the ladybug is away from the center of the record as it's spinning, and that, of course, is our radius. So 10 centimeters times 5 pi over 6 radians per second, and thankfully it's also in seconds, so we don't have to do any fancy conversions. That's going to be 50 pi over 6, right? Or 25 pi over 3 centimeters per second. Okay, and so this asked me both for my omega and for my v. The next question is going to do pretty much the same thing, okay? An object is traveling around a circle with a radius of 2 meters, okay? if in 20 seconds the object travels 5 meters, what is its angular speed? Well, it basically gave us arc length, and it gave us time. So arc length over time should give us something, right? Now, in this, okay, so basically we remember that its angular speed, omega, is going to be theta over t, okay? Linear speed, again, is going to be v over t, which is also r, s. This is supposed to be s. S over t, which is r theta over t, which is r omega. Now the question is, which one is easiest to find first? Well, it doesn't really matter how we riddle this out. I would actually go for the linear velocity first. Okay, largely because we already have our s. That is how far it traveled, right? That is the arc length. Then we also have our time. If we have s and t, we can find v. So v is equal to 5 meters over 20 seconds. Well, that basically is 1/4 meter per second. So if we have v, right, and we want omega, we know that v is equal to r times omega, okay? And therefore, omega is equal to v over r. Is it not? All we have to do is just, to get omega by itself, is divide both sides by r, right? And so in this case, if we have v, we have 1/4 meters per second, and we're going to divide it by 2 meters. That gives us 1/8 blank per second. Okay? 1/8 blank per second. Well, what do we put in that blank? Well, we're looking for angular speed. And remember that unit, that pseudo unit that went nowhere because it wasn't really there in the first place, so it kind of disappeared. Well, here it kind of reappears as radians right there. And so here's my v, here's my omega. And remember, radians can disappear and reappear because it's not really a unit. It kind of is, it kind of isn't. But since it's a unit that simply communicates sort of the fraction of a full revolution of a circle, it'll disappear and reappear, and you have to basically watch it appear and reappear based upon your knowledge of what it is that you're really looking for, right? And I don't particularly enjoy sections like this because they're just highly formulaic, and the problem with formula sections is we sometimes rely just on pure procedure instead of truly understanding what's going on. But I am trying to talk through them in such a way that you can appreciate what is really going on in all of these various problems. That's it for this first day of work that we are going to have. I hope these videos have solidified the things that we talked about in class. I hope that they were a useful supplement, and I hope that they aided you in getting the homework done. Please, as always, do give me feedback. It's going to take a little while for us to get used to each other. That's just the name of the game. It's just the nature of the beast. But we will. But I, of course, will always. I'll always listen to any feedback that you have, and if I think that it is going to help the vast majority of the people, I will try and incorporate it into future instructional videos. But like I said in a previous video, if you have any questions, please do reach out to me, shoot me a message on Teams, and I will try to get back to you as soon as I can. Bye.